All right, folks, we're going to go ahead and talk about a little bit of how we produce energy. Now, a number of these slides I'm not going to bother to read to you because I consider that to be insulting to your intelligence. Make sure you're going through it. This is going to go back to things that we covered in exercise physiology that you would have had in just physiology, chemistry classes, and otherwise. So let's make it happen. First and foremost, we produce energy in our cells. Why do we need energy? Because it turns out we like to perform work, and work requires some type of energy to go ahead and allow us to perform it. And this is going to be typically done by ATP, the universal energy carrier in the cell. And so we constantly are going to be turning over this ATP, so we need to create it more out of our other macronutrients, protein, carbs, and fats. And then we're going to store it in carbohydrate form and fat form. Technically, we're storing it in protein form, but that's also the equivalent of taking pieces of the car apart to use it as fuel. So that's not really a good choice. And then all the different ways we're going to regulate it. Now, think back to good old exercise physiology, the basics of how muscles contract, and that's a lot of ATP to allow those myosin cells to ratchet. And so we're turning over energy a lot anytime we're moving. Now, different muscle fibers types are going to use different fuels more predominantly over than others. When you guys are watching this, feel free to pause the video, and that's going to give you more time to go ahead and look at this. And it's all relative to the slow fibers. So you can see how the fast fibers are faster in certain ways and slower in others when it comes to what type of fuel we're going to be able to utilize more efficiently. Now, this is how we're going to convert from one type of essentially macronutrient to another. We can always convert proteins and carbs into fats. We can't really convert fats into anything else. We can use glycerol to convert that into an intermediate that can then be converted into pyruvate. So just understand kind of how this flow chart works from one side to the other. Now, we are going to utilize carbohydrates as fuel in any type of moderate to high intensity exercise. It tends to be the thing we prefer to use. We have the anaerobic and aerobic forms of this, and hopefully this is going to be somewhat a bit of a refresher, and you can look on the right and see the total amount of energy that you're producing when you do so aerobically. So here's glycolysis. Comes in 3 stages where we have activation, cleavage, and then phosphorylation of ADP. So you can see how we have the first 3 steps, one more where we cut it into 2 and then move on through. Understand the major rate limiting, which is going to be hexokinase and phosphofructose kinase, and then also how we're going to be generating ATP, how we're going to be using ATP for activation, and then how we're going to skip it if we're starting from glycogen. So just look at it, make sure you understand kind of how all this flows together, and then finally the fork in the road at the end of whether we're doing this aerobically going into acetyl-CoA or anaerobically and going into lactate. Now, we are going to utilize fats as fuel for everything that is super low intensity or just staying alive. This is going to be things that we're using at very, very low levels, and it's going to go through a process known as beta oxidation, and that occurs in the mitochondria. Now, there's a number of hormones that are going to help us release fatty acids from our fat cells. So we're going to be able to drop them into the bloodstream and then have them be able to be taken up anywhere else in the body where we need them for energy. And then it's insulin, which is going to be the one that helps us with storing fat. So fun facts. Now, this is the Cat1-2 shuttle of how we actually get fatty acids into our mitochondria. This tends to be a bit of a rate limiter, and this is also where you see the use of carnitine. That's going to help shuttle it into the cell. As you've probably seen carnitine before on different types of energy drink supplements and otherwise that are supposed to help increase energy. Now, here we're going to have the basics of how that beta oxidation is going to occur inside the cells. We have to get the fatty acids into the mitochondria, how glycolysis is going to occur in the cytoplasm or the cytosol of the cell. And then once we get into acetyl-CoA, that's going to occur inside of the mitochondria, the citric acid cycle in its entirety there, and protein converts into a lot of individual things. Don't worry about it. Now, the citric acid cycle is where we're going to take and break down things into NADH, FADH2, 1-GTP, which converts immediately into an ATP, and some more NADH. Oh, and carbon dioxide. And then all of this is going to then flow into the electron transport chain where it's going to be the final electron acceptor and where we're going to have energy production. Once again, guys, I'm going too fast. Please, please, please take your time. Look at the slides. Now, it turns out we are going to be able to make ATP really quickly because our first energy system, that ATP PCR system, is very fast with its turnover, but its total amount of resynthesis or how we're going to be able to replenish it is much, much slower. Now, what we have on the left, that's the ATP PCR, and we have on the right is going to be that anaerobic glycolysis, and how they're both going to be able to give us a pretty high amount of energy, but it's going to take a little bit to get up to speed. Now, when it comes to carbohydrates and all these fuels, we've got a lot of different places they come from. We store the fat, obviously, anywhere in the body where we have subcutaneous fat. We're going to store our glycogen, not just in our muscles, but in our liver. And then we're going to be utilizing other fuel sources that are already stored inside of the muscle. Now, if we're happening to be working out at really, really high intensity, we're probably going to have a cause of fatigue because of too much metabolic byproduct accumulation. So that's going to be too much increases in protons from the increased amount of lactate, which can be dropping our pH, and then a lack of ATP availability. When we're talking about fatigue from very long duration exercise, now we're talking about glycogen depletion, low blood sugar, and possibly even intracellular fatty acid stores really, really going down to low levels. And notice, guys, the resynthesis rates, given the duration that we're doing. And remember, no energy system is ever working in a vacuum. We're always going to use a little bit of each of them, no matter what we're doing. Now, what we have here is really, really long duration work, which is obviously if we're keeping the same intensity up for, notice, up to 2 hours, we're going to see that decrease in blood glucose. We are going to be freeing up more fatty acids to use them as fuel, and we are going to be decreasing the amount of glycogen that we're going to be having inside of the muscles that are exercising. Remember, it's specific to what we're doing. And the higher intensity that we're working at, the faster that we are going to be depleting our intramuscular glycogen levels. And the higher the intensity we're working at, the more glucose we're going to be taking up. I don't want to insult you guys. The graphs are pretty easy. Now, when it comes to the amount of energy that we're using, as our duration increases, we are going to, and we're maintaining the same intensity, we are going to start utilizing fats more as a fuel. We are going to be leaning less and less on the muscle glycogen. We're going to be pulling a little bit more and more, and then notice we're going to peak a little bit with the plasma glucose. Now, when it comes to the actual exercise intensity, so when we look at the graph on the bottom left, as we kick up our intensity, we are going to start to utilize more and more intramuscular stores of energy, being that the muscle glycogen and the triglycerides inside of it, and we're not going to be able to get as much from our blood plasma, glucose, and fatty acid level. And what I like on the graph on the right, you can really see that crossover point of how at lower intensities you see the vast majority of energy is being produced by fat, and then we see how we're slowly going to start to use more and more muscle glycogen, along with relying more and more on blood glucose once we talk about having people go at higher velocities. Excuse me. So, how much energy we store inside of our body? Well, it turns out not a lot of carbohydrate, but a lot of fat. Your average person is really only going to have about maybe 2,000 calories worth of carbohydrates stored inside of their body. And this is for a 154-pound European male. Yay for standardization. But even somebody that's relatively lean can quite easily have literally almost 100,000 calories worth of energy via fat stored in their body, which is going to allow them to exercise for really, really long intensities. But obviously, it's not how we're going to do it. And then once again, we do have protein as a source, but we don't use it too much because that's the equivalent of, once again, disassembling the car to keep the car running. Not a good long-term strategy. So how are we going to regulate this? Well, we have a lot of intracellular factors that are going to do it, and this is through negative feedback. We have a number of hormones that are going to affect our energy availability. Remember, insulin is going to be the one that's going to be helping to store carbohydrate, but it's not going to be, it's going to also be limiting our ability to utilize fats as fuel. Glucagon, catecholamines, meaning epinephrine, norepinephrine, growth hormone, cortisol, all of those are going to help free up energy, along with IL-6 is going to give us some changes. Now, metabolic adaptation exercise training, the more that we train, specifically the energy systems that we train within, the better we're going to be at using them. Now, here's the areas that these hormones come from, what they're going to do, and the actions. Take your time, read through it, don't rush it, pause the slide. This is how a hormone works. That happens to be a steroid hormone because it works directly inside of the cell. This is how a protein-based hormone works. Yay. And this uses secondary messengers to affect change inside of the cell. And this is the cool thing, that exercise, along with increasing calcium amounts inside of the cell, is going to cause glucose 4 receptors to translocate to the cellular surface. So we literally become more sensitive to carbohydrates. Now, insulin itself is also going to do this, but that's why exercise is a big component here. Make sure you understand what GLUT4 receptors do. And yeehaw, if we happen to be exercising and we're taking in a greater amount of carbohydrates, we tend to do a better job with exercising for longer periods of times. Yay, science. And when you happen to be in better shape, you actually don't have to use as much hormones in order to keep yourself going for as long, because it turns out it's not as stressful because you're in shape. And here is going to be all of that negative feedback. So take your time going through the slide and really seeing how one hormone is going to be, or sorry, one chemical that is being produced, it can obviously be hormones, are going to be influencing the increasing the effects or decreasing the rates that different enzymatic processes are occurring inside of the cell. Take your time, don't rush it, make sure you understand how all this works together. So I like to think of the energy systems as a pyramid. At the bottom, we have our beta oxidation. Then we're going to be moving up. And now as we go up, we're going to be able to produce more and more energy at a faster rate. But notice it's not as broad. We don't have as great of a capacity to produce that energy for long periods of time. So hence, when we're working with athletes, we want to keep in mind that we're trying to train all of the energy systems, honestly, but we're going to emphasize one more so than another. And when in doubt, having a better aerobic capacity is probably going to help you more than hurt you. So thanks for listening. Sorry for doing it so quick, but have a great day, and we will make sure that we elaborate more on this whenever we meet as a class. Bye-bye.